Welcome everybody. Today we will talk about material balance calculations for single units without reactions. We have already looked at many different processes. Today we will look at one of the most common processes seen in all chemical and biochemical industries. It is the filtration process. A feed solution or a slurry which enters into the filter is separated into two different streams during a filtration process. The liquid stream which leaves the system is called as the filtrate, and you also have a filter cake which is the wet solids which leaves the system. So, the filtrate, which is the exit liquid, is solid free, and the filtrate contains all the soluble components which are accompanying the liquid which enters into the filter. Filter cake can actually contain some of the liquids. The filter cake is not always dry. It will always contain some of the liquids which are coming along with the slurry entering into the filter. Imagine this process where you have water and sand mixture. So, this slurry, when it is filtered, you will have the liquid which is water collected as the filtrate, and you would have the sand which is collected on top of the filter paper. So, this sand will not be dry. It will have the accompanying water along with it. So, now there is an important point which needs to be remembered when we talk about a filtration process, so that we can perform material balance calculations. It is the concentration of dissolved components in the filtrate and the liquid accompanying the filter cake are the same. What do I mean by this? Consider this example. So, extending the example which I gave earlier, you have now a slurry which contains 10 grams per liter of sand dispersed in a salt solution. Instead of just water, now let us consider the salt solution in which the sand is dispersed. If the dissolved salt concentration in the slurry is 100 grams per liter, then the salt concentration in the filtrate, which contains only the solution, will also be 100 grams per liter, and the liquid accompanying the filter cake, which is the sand, will also contain 100 grams per liter. So, this will be true if the sand, which is the component, solid component present in the slurry, does not absorb the dissolved components. If there are other components such as filter aids which are added, then you can expect that the dissolved components can be absorbed by these filter aids or other components which are added, in which case the concentration of the dissolved components in the filtrate and the liquid accompanying the filter cake will still be equal. They would just be lower than the concentration in the feed which is entering into the filtration system. So, knowing this, we would be able to perform material balance calculations for a filtration process. Let us now look at an example problem for filtration. A fermentation slurry containing Streptomyces canamyceticus cells is filtered using a continuous rotary vacuum filter. 120 kilograms per hour slurry is fed to the filter. 1 kilogram slurry contains 60 grams of cell solids. To improve the filtration rates, particles of diatomaceous earth filter aid are added at a rate of 10 kilograms per hour. The concentration of kanamycin in the slurry is 0.05% by weight. Liquid filtrate is collected at a rate of 112 kilograms per hour. The concentration of kanamycin in the filtrate is 0.045%. Filter cake containing cells and filter aid is continuously removed from the filter cloth. What is the percentage of liquid in the filter cake? If the concentration of kanamycin in the filter cake liquid is the same as that in the filtrate, how much kanamycin is absorbed per kilogram of filter aid? So, now go through the problem one more time, so that you are familiarized with all the terminologies and all the information that has been given to you. After you have completed this, let us start with identifying the basis for this problem. What would be the basis? What would be the suitable basis for this problem? In this problem, there are multiple flow rates which have been given, which means we can either use the given flow rates as the basis, or we can use per hour as the basis. For calculations, I have used 1 hour as the basis and performed the calculations. So, let us go about solving this problem. Basis is 1 hour. Let us draw a flow chart which would explain the problem statement given. We have a filtration system which has an input which is the slurry that is being fed to the filter at a rate of 120 kilograms per hour. Because I have assumed a basis of 1 hour, I would write this as 120 kilograms of slurry being fed. This has been given that 60 grams of cells are present in 1 kilogram of the slurry which is fed. In addition, we also know that the slurry contains 0.05% kanamycin in the dissolved component. In addition to the slurry, we are also adding a filter aid, which is diatomaceous earth. This is entering as 10 kilograms per hour. Considering the basis of 1 hour, we write this as 10 kilograms. Now, we would have two exit streams, one being the filter cake which contains the cell solids and the liquid which is accompanying the filter cake. So, we write that as filter cake which contains X0 cells, Y0 kanamycin and Z0 filter aid and the accompanying water which I am just calling as W2 out. So, the other stream is your filtrate. The filtrate would contain only the dissolved components and water. It has been given that the filtrate is collected at a rate of 112 kilograms per hour. So, considering the basis, I am writing this as 112 kilograms, and this contains 0.045% kanamycin and the rest is water, which I am just writing as W1 out. So, all the information that has been given to you in the problem has been entered into this flow chart. Now, if you look at the concentration of kanamycin, which is the dissolved component in the filter feed and the filtrate, you would see that there is a decrease, which indicates that some of the kanamycin which has been fed to the system has actually been absorbed by either the diatomaceous earth filter aid or the cell solids itself. So, the second part of the question actually asks for the amount of kanamycin which could have been absorbed by the filter aid, indicating that the filter aid that has been used actually absorbs some of the kanamycin which has resulted in this decreased concentration. But we also know that in a filtration, the concentration of kanamycin or the dissolved component would be the same in the filtrate and the liquid accompanying the filter cake. So, knowing all this information, let us go about solving this problem. Here is the flow chart which we drew, so in more legible fonts. Now, let us start with the balance equations. The first balance we write would be the total balance. The total balance equation for this system would be, would basically be input equals output, because it is a system in steady state leading to accumulation being 0, and as the system does not have any reactions happening, generation and consumption terms will also be 0. So, input equals output. So, this would mean Si plus Ai equals C0 plus F0, where Si is the slurry and Ai is the filter aid entering, C0 is the filter cake leaving the system and F0 is the filtrate leaving the system. We already know the values of Si, Ai and F0. So, that is 120 plus 10 is equal to C0 plus 112. So, this means C0, which is the filter cake, is 18 kilograms. So, the mass of the filter cake which would be leaving the system would be 18 kilograms. Now, we can then write component balances. So, the component balance we can start with would be cell balance. Cell is entering only through the fermentation slurry and is leaving only through the filter cake. We do not know the amount of cell which is leaving through the filter cake, we have just written the mass to be X0. So, this would mean input equals output, implying 6% of the fermentation slurry, which is 0.06 times 120 is equal to X0. So, x naught is equal to 7.2 kilograms. We can continue writing component balances. For filter aid, we can write the component balance as again input equals output. So, the input comes only through AI and the output leaves only through C naught. So, the amount of filter aid leaving the system through the filter cake has been written as Z naught. So, AI equals Z naught, implying Z naught would be 10 kilograms. So, we can still write a balance equation for kanamycin and for water. So, let us first write the kanamycin balance. So, again it would be input equals output, and input for kanamycin is 0.05% kanamycin in the fermentation slurry. So, you would have 0.0005 times 120 entering the system, which is equal to the kanamycin which is leaving through the filtrate and the kanamycin which is leaving through the filter cake. So, this would be 0.00045 times 112 plus y naught. So, based on this equation you can calculate y naught as 0.01 kilograms. What you need to understand here is this y naught term contains kanamycin which is present in the solution along with the filter cake, and also the kanamycin which has been absorbed by the filter aid. So, both the components are accounted for in this one term which is y naught. Now, the next balance equation we can write would be the water balance. Again input equals output. So, input is through water which is coming in through the slurry. So, we would call that Wn is equal to W1 out plus W2 out. Water is entering the system through the fermentation slurry. It has been given that the concentration of kanamycin in the fermentation slurry is 0.05% and the concentration of cells in the slurry is 6%. So, the rest has to be water. So, knowing that, we can calculate the mass fraction of water as 1 minus 0.06 minus 0.0005 times 120. So, this is the mass of water entering the system. So, water is leaving the system through two different streams. In the filtrate, the concentration of kanamycin is given as 0.045%, which means the rest would be water. So, the mass fraction of water would be 1 minus 0.00045 times the mass which is 112, giving you the total mass of water leaving the system through the filtrate. So, we need to calculate the mass of water leaving the system through the filter cake, which is given as W2 out. So, from here we can calculate W2 out as 0.79 kilograms. So, 0.79 kilograms of water leaves the system along with the filter cake. The first part of the question was to calculate the percentage of liquid accompanying the filter cake. We now know the total mass of the filter cake and also the amount of water which is accompanying the filter cake. So, based on this we can calculate the percentage of liquid accompanying the filter cake as percentage liquid in C naught is equal to 0.79 divided by 18, which is the total mass C naught, times 100. This gives a percentage of 4.39%. So, this gets us the final answer for part 1. For the second part of the problem, we need to calculate the mass of kanamycin which is absorbed by the filter cake, so which contains the filter aid. So, now for doing that we need to know how much of kanamycin is actually present in the liquid accompanying the filter cake and how much is actually absorbed by the filter aid in the filter cake. We know that the concentration of kanamycin in the filtrate and the liquid accompanying the filter cake are the same. With this information, we can actually calculate the amount of kanamycin which is leaving the system with the water accompanying the filter cake. So, we know the mass of water is 0.79 kilograms and the concentration of kanamycin in this would be 0.045%. So, using this information, we can calculate the mass of kanamycin in the liquid present in C naught, which is the filter cake, would be 0.00045 times 0.79 kilograms, which is the mass of water. So, the total mass of kanamycin leaving in the liquid is 3.6 times 10 power minus 4 kilograms. So, based on the material balances which we had performed earlier, we know that 0.01 kilograms of kanamycin is actually present in the filter cake. So, out of this 3.6 times 10 power minus 4 kilograms is leaving in the liquid, which means the rest is actually being absorbed by the filter aid. So, the amount absorbed by filter aid would be .1 minus 0.1 minus 3.6 times 10 power minus 4, which gives you a value of 9.6 times 10 power minus 3 kilograms of kanamycin. So, this is the total amount of kanamycin which is absorbed by the filter aid. The problem actually asks for the amount of kanamycin which would be absorbed by 1 kilogram of filter aid which is added. So, this divided by 10 would be the required answer. Required answer, which is the mass of kanamycin absorbed per kilogram of filter aid, would be 9.6 times 10 power minus 3 divided by 10, giving you 9.6 times 10 power minus 4 kilograms per kilogram. So, this would be kilograms of kanamycin per kilogram of filter aid used. So, with this we would have solved for all the required parameters that have been asked. Hopefully, you were able to follow the procedure for calculating these balances. With this, we will conclude today's lecture, and we will continue in this future classes where we start looking at systems where more than one units exist. So, until now we have been looking at simple processes with single units, but in most cases you would see multiple processes, and we will look at how to approach material balances for systems containing more than one operation. Thank you.